And our next speaker is Grigory Chirkov. He's a fifth-year PhD student at Princeton University, and he works with David Wentzlaff. His research is on computer architecture, modeling on FPGAs, and analyzing architectures and other modeling activities. And he's interested in future multi-chiplet architectures. He's currently looking for summer internships in industry. So reach out to him after his talk if you are looking for interns this summer. Okay, take it away.
Thank you for this introduction. Thank you everyone for coming to my talk. My name is Grigory, and today I would like to present my work with my advisor, David Wentzlaff at Princeton University, called SMAPPIC, Scalable Multi-FPGA Architecture Prototype Platform in the Cloud. So one of the ways to evaluate a new architecture is to build an FPGA prototype of it. And during the classical workflow, you would take your design, write an RTL description of it in Verilog or VHDL, and then port it to an FPGA. And compared to software simulation, there are two big advantages: speed and accuracy. However, there are three big problems that prevent a widespread adoption of FPGA prototyping in our field. The first one is complexity. Researchers usually do not want to spend extra time writing Verilog code for their architectures. Second, it is expensive, and the big FPGA needed for large-scale architecture evaluation can cost tens of thousands of dollars. And finally, it is not scalable because the amount of logic you can emulate is restricted by the size of the FPGA. SMAPPIC solves all of these three problems. So let's take a closer look at SMAPPIC's design. SMAPPIC is based on three big pillars. The first one is open source code base. We base our work on OpenPython or BYOC framework for heterogeneous systems research. We also provide an open source code base, so you can take our code as a template for your designs, and you can use our parameterizable Verilog to change the parameters of the system. So this way we are trying to make it easy to prototype your designs in FPGA. Second, we use cloud FPGAs through AWS F1 infrastructure. By doing this, you can access your FPGAs on demand, pay as you go, and you can access them remotely from anywhere in the world. And finally, the biggest characteristic of our work is we distribute design over multiple FPGAs through a novel interconnect, making your prototypes scalable. So let's take a closer look at the interconnect. As I just said, we base our work on BYOC framework, and this is a model of many core system. We then put it into an FPGA, and if we have 4 FPGAs with these frameworks, they're not really connected and they cannot exchange data between each other. What we would ideally want to do is to just extend the BYOC interconnect across the nodes, but we simply cannot route wires across the FPGA boundaries. What we can do, though, is we can use included PCIe interconnect of the host machine. So what we did is we designed an internode bridge that encapsulates BYOC traffic inside the PCIe traffic. We add traffic shapers on top of this internode bridge to decouple target interconnect properties from PCIe properties. We measured the minimal round-trip latency of this interconnect at 125 cycles at 100 megahertz target frequency. And this is actually great for multi-socket and multi-chiplet modeling. So what I was referring to before as nodes is actually separate chiplets or separate sockets of your system. And the whole prototype is actually a prototype of multi-chiplet or multi-socket system. So let's take a look at how interconnect works. We're going to take an example, take a look at an example of private cache miss. And for the sake of the example, we're going to assume that the private cache in tile 4 generates a cache miss. And in this case, the read request is sent to the home L2 slice. Again, for the sake of the example, we're going to assume that the home slice is located in node 3. So in this case, because our home slice is on the another node, the request is going to be routed first towards tile 0 and then northbound into the internode bridge. There, the request is going to be encapsulated into PCI requests and set towards node 3. The response package is going to go through the same route. It's going to go through the PCIe infrastructure and eventually arrive to the receiving side of internode bridge. There, the traffic of BYOC is going to be decapsulated and routed back towards tile 4. We had to do a couple modifications to BYOC to enable the multi-chiplet capabilities. The first one, L2 slice interleaving. We use low bits interleaving inside the node for lower distribution, and we use high bits interleaving between the nodes for software NUMA control. Second, we have a local DRAM controller inside each node. So the traffic from L2 home slices are local inside the node, and they do not cross the node boundaries. Now let's take a look at use cases that SMAPPIC enables. The first one, the big one, is large-scale architecture modeling. Using SMAPPIC, we could build a system with 48 Ariane cores. We did this by building 4 chiplets, each with 12 cores. And we're proud to announce that this is the first 48-core, 64-bit RISC-V system with coherent shared memory ever made. We configured the system so that we have 100 cycles round-trip latency between cores on the same node, and 300 cycles round-trip latency between cores on different chiplets. So as you can see on the chart on the right, our system has an explicit NUMA properties. And then we use this prototype to evaluate NUMA implementation in Linux RISC-V kernel. We use the integer sorting benchmark for this. The first chart here shows the performance scaling with the number of threads. And as you can see, as we could expect, NUMA mode enabled produces better results than NUMA mode disabled. What's also interesting here is that with NUMA mode disabled, we actually see a slight performance decrease after 24 threads. Another study we did is we studied how the allocation of the threads influences the performance results of the benchmark. So we fixed the number of threads to 12, and we distributed them across 1, 2, 3, or 4 active chiplets. And we see the expected results with NUMA mode enabled. The performance decreases slightly because we basically increase the effective distance between the threads. What's interesting here is performance actually becomes better with NUMA mode disabled. And after closer inspection, we saw that what's actually happening here is the probability that the thread is collocated with data increases if we distribute the threads across more chiplets. So this is a kind of study that is possible, uniquely possible in SMAPPIC. The second one is accelerator verification, evaluation, and hardware-software co-design. To demonstrate this, we re-evaluated Maple engine for indirect memory accesses in multi-core environment. And we saw the same performance as the authors of the original paper. But what's interesting here is we actually found a bug in the RTL implementation of the framework. The engine stores the physical core ID at the beginning of the task. And while this works fine in bare metal settings or in settings with low core count that the authors of the original paper use, it does not work when you have a lot of cores and you run your experiments on top of OS because of the thread migration. And again, this is an example of the use case that is uniquely possible with SMAPPIC. Next one is in situ studies of custom architecture interaction with cloud infrastructure. If you think about it, SMAPPIC model is actually a full chip running inside the AWS data center. And this allows you to model interaction between your custom architecture and the other stages of the cloud pipeline. To demonstrate this, we compiled a backend server to RISC-V and ran it on SMAPPIC. We further integrated SMAPPIC into the cloud pipeline that uses AWS Lambda as a front end and AWS S3 as a backend. And this setup shows you how you can replace this SMAPPIC model with your SMAPPIC model and evaluate your custom architecture in the cloud. The last but not least is cost-efficient architecture modeling. In cloud, time means money. So you actually really want a fast modeling experience so that you pay less money for your modeling. We did the study by finding smallest suitable AWS instance for each modeling type and multiplying price by modeling time. And what we found out is that compared to SMAPPIC, Gem5 is about 1,000 times more expensive, Sniper is about 2 times more expensive, and Fireteam is about 3 times more expensive. And this brings me to the end of my presentation. Let's quickly go through the key points of my talk. SMAPPIC, Scalable Multi-FPGA prototype platform in the cloud, tackles 3 issues with classical FPGA prototyping: cost, complexity, and scalability. SMAPPIC's 3 main approaches are the use of cloud FPGAs, open source parameterizable code base, and logic distribution across multiple FPGAs using the novel interconnect. SMAPPIC opens new research opportunities and makes FPGA prototyping more accessible for the whole academia. And thank you for your attention. I would be happy to answer your